moving along on our journey with the structure of the atom, elements, compounds, and so forth, we want to go into bonding between two different atoms. And we're going for kind of a broad brushstroke. Suffice it to say that chemical bonds are attractions between two different atoms. I like to think of them almost like a glue. It gets them to stick together. This occurs through interactions between electrons of two different atoms. And usually that's in the outermost like energy level. We didn't really go into electron kind of structure, but basically the outermost electrons in an atom are the ones that are interacting to make the bonds. So a covalent bond is when different atoms share their electrons. The valence shell is the outermost shell in the atom. So covalence means that there's, you're getting sharing of electrons between the two, and almost like the valence shell it's kind of like combining together. So here we have like a depiction of how really that almost you kind of have this fuzzy area is the electron cloud, and as we're bonding two hydrogens together, you get kind of the melding together of the two electron clouds to make H2, which is a molecule. It's not a compound. Compound would actually take two different types of elements. So, we can have, when we do bond them together, we can have a single bond or a double bond or even a triple bond. Single bond is one pair of electrons are being shared. Double bond is we have two pairs, and triple bond's three. Here's a number of different depictions. You can see, we can actually draw out all the electron shells. We can just draw a line that each line represents two electrons. You got something called a space filling model, so it looks like it's in 3D. So we have a number of different, we have like hydrogen, oxygen, water, methane. You can see how they're differently depicted, but these are all covalently bonded molecules, and it's important to know that when you have a covalently bonded molecule, you have bonds between what we call two non-metal elements. So sometimes various atoms have a lot of what's called electronegativity, and that's its ability to really kind of hold on to electrons when they're in a covalent bond. So the more electronegative an atom is, the more strongly it pulls shared electrons. The most electronegative element is fluorine, but oxygen is really fairly electronegative. And when we're making these covalent bonds, sometimes there's unequal sharing. And when we get unequal sharing, we will call that like a polar covalent bond versus equal sharing, which is a non-polar covalent bond. And usually this occurs when you have a big difference in electronegativity. If you have two really electronegative elements, they'll form actually a non-polar covalent bond. But when you have something, say like hydrogen, which has fairly low electronegativity, and then oxygen has a high electronegativity, you're going to get a polar covalent bond. If it's that huge of a difference, it ends up becoming our next bond, which is ionic. But anyway, here you see this picture, and we see arrows going towards the oxygen, and that's referring to the unequal sharing. Oxygen is holding on to electrons for a long time. compared to hydrogen. And as a consequence, remember the electrons are negative. As a consequence, that's making the oxygen act negative because the electrons are spending more time with oxygen. And then the hydrogen acts a little bit more positive. Our next bond is a ionic bond. And this is when you actually have like permanent kind of donation and acceptance of electrons. An element will just dump off its electrons on another one. But it ends up being kind of mutually beneficial for both. So here we have sodium chloride. Sodium has this electron on the outside. Chlorine actually needs one more, so sodium just kind of dumps it off to chlorine. And that's going to make sodium positive in charge because it actually got rid of an electron. And then chlorine will be negative. So sodium's getting rid of a negative charge and makes it more positive. Chlorine's gaining a negative charge that makes it more negative. So if you ever heard this term cation, that's a positively charged ion. The cat has a plus in the middle. Anion is a negatively charged ion. But then when you get these two, like a cation and an anion, when they're sticking together, it's called an ionic bond. Well, how do they stick together? This is through opposite electrical charges. You have a positive one and a negative one. And then since the opposite electrical charges attract each other, they stick together. And ionic bonds are actually the most powerful ones. Compounds that are made are salts, so table salt's a great example. And then this is when a metal and a non-metal will react together. Here's the crystal of sodium chloride. Then we have some weak chemical interactions, and these aren't, they're called bonds, but there's not necessarily anything that's making these two things stick together for any significant amount of times. So when we have something that has polar covalent bonds, it has hydrogen in it, and that kind of is attracted to another molecule, we call that a hydrogen bond. So here's an example. We have water, H2O. And you saw this before where the electrons are spending more time with oxygen. Then ammonia is NH3, and in this case, the electrons are spending more time with nitrogen. So since we have a partial positive charge on hydrogen and a partial negative charge on nitrogen, you get this attraction between the two. We call that a hydrogen bond because this has hydrogen in it. So does ammonia does too. Then we have something called van der Waals interactions. They're very similar to hydrogen bonds, except that they don't really have, a compound with hydrogen in it. Whoops. Anyway, I was just going to say that it's very similar to hydrogen bonds, so we don't have hydrogen. And then I thought I had a picture of a gecko in here, but due to these van der Waals interactions, a gecko can kind of like climb walls and stuff. One of the things that I will kind of beat on throughout the semester is that shape's really important, and here we can see how whatever we make shapes and so on, but molecular shape actually determines a lot of things, and one of which is kind of how our own cells are able to read and I shouldn't say call it reading, but basically they receive like messages and then can kind of pass that on. But the way in which the messages are received is through shape. There's like a receptor, and then if something fits in that receptor, then the message is received. If it doesn't fit in the receptor, well then there's no message has been received. So here we have pictures of endorphins and morphine. Endorphins is thought to cause runner's high, but it also kind of deadens pain if your body gets a release. And then we know morphine deadens pain. You can see they're very similar on structure. And then in the brain, endorphins, well, actually, I should say there's endorphin receptors that, endorphins that you produce land on there, but then morphine also will land on endorphin receptors. And as an interesting aside, morphine was actually how do you get back here? Morphine was the first thing that was discovered, and then the scientists thought, well, if you just wouldn't randomly have a receptor that receives morphine, so maybe there's a molecule in our body that is similar, does similar things, has a similar shape, and they found endorphins. Oops. But you can see they're similarly shaped, and then they have a similar effect on the body. All right, and that's chapter 2.3.